In this lesson, we'll learn an alternative method to find volumes of solids of revolution called the shell method. So consider the example. So suppose we try to find the volume of the region bounded by the curve 2x squared minus x to the third about the y-axis. Why is this so hard? So if we use the method of the previous section, we will slice perpendicular to the axis of rotation, so we'll slice this way. And to do so, we're going to have to find an outer radius and an inner radius. So you need to figure out where this maximum point is, solve this equation for x, and that's not so hard. So the problem is this is not an easy equation to solve for x. So we will be able to find the volume of the solid generated when this region is rotated about the y-axis very easy using the method called cylindrical shells. So consider the following problem. So suppose we have the region bounded by a curve y equals f of x between a and b. When you spin this region, you get something that looks sort of like what's in the picture next to it. Now, what we will do instead is, instead of cutting our slices horizontally, we're going to cut them vertically like this. And we're going to spin those instead. And when you spin those, you get something like this picture here. So what we find the volume of in this case is a hollow cylinder with a certain thickness. So the first thing we're going to figure out is how to find the volume of what's called a shell. So the volume of a single shell. Before we find the volume of the entire solid, we're going to find the volume of a single shell. So we'll call this V sub S. So the volume of a single shell will equal the volume of the outer cylinder minus the volume of the inner cylinder. And the volume of a cylinder is pi r squared h, the area of the base times the height. So the area of, so for the outer one we will have pi r sub 2 squared h. The inner will be pi r sub 1 squared h. If I take out the greatest common factor, which is pi h, I have pi h times the quantity r2 squared minus r1 squared. And I can then factor that, r2 squared minus r1 squared, into r sub 2 minus r sub 1 times r sub 2 plus r sub 1. And then notice that r sub 2 minus r sub 1, that's actually delta r, or the change in r. So we have pi h times delta r, and I'm going to rewrite r2 plus r1 as 2 times r1 plus r2 over 2. And that's not actually different because those 2's really would cancel. Now notice that r1 plus r2 over 2, that is the average radius of the shell. So little r is r1 plus r2 over 2. So the volume of a shell is 2 pi lowercase r h delta r. And it's useful to think about that in the following way. This is the circumference. H is the height. And delta r is the thickness. Now if we return to our example for a curve between A and B that we're rotating about the y-axis, so you're going to let x sub I star be somewhere in the interval xi minus 1 xi. The volume of the ith shell will equal 2 pi. Now in this case, r is the distance from the axis of rotation to where you make your slice. That's actually x. The height will be f of x sub I star, and the thickness will be delta x. And to find the total volume, you add all these shells up. So the total volume V will be given as the limit as n goes to infinity And the sum from I equals 1 to n 2 pi x f of x sub I star delta x. And this, by definition, produces an integral. The results on the previous slide tell us that to find the volume of a solid by rotating the region underneath the curve y equals f of x between a and b about the y-axis is given by v is equal to the integral from a to b 2 pi x f of x dx. And once again, it's helpful to think about this formula as circumference, height, and then thickness. So let's return to the example of rotating the region y equals 2x squared minus x cubed about the y-axis. So the picture there looked like this, crossed at 0 and at 2. So here is my typical shell. So I'll find my volume by integrating from a to b, so 0 to 2. Now the circumference will be 2 pi x. So circumference, height. The height is given by the equation of the curve, 2x squared minus x cubed, and the thickness is dx. And that's actually quite easy. 2 pi integral 0 to 2. That will be x cubed minus x to the 4th once we distribute that x. Anti-differentiate. And we will have 1/4 x to the 4th minus 1/5 x to the 5th, evaluated from 0 to 2. So that's 2 pi times 1/4 of 16 minus 1/5 times 32 and minus 0. And that gives you 16 pi over 5. In this example, we will rotate a region between two curves about an axis. So we are going to find the volume of the solid obtained when we rotate the region bounded by 3 plus 2x minus x squared and x plus y equals 3 about the y-axis. So first you have to plot the parabola 3 plus 2x minus x squared. So we know that there is a y-intercept of 3. So you plug in 0, you get out 3. Now maybe you remember this formula from Algebra 1. X equals negative b divided by 2a finds the vertex. So that'll be negative 2 divided by 2 times negative 1. So that is x equals 1. And when x equals 1, y is equal to 3 plus 2 minus 1, which is 4. So at 1, parabola's at 4. And that's the line the parabola is symmetric about. So you can reflect that point from the y-axis over. And when you input 3, we get 0. And input negative 1, you also get 0. So there's your parabola. And then x plus y equals 3 is the same thing as y equals 3 minus x. So it's a line with y-intercept 3 and slope negative 1. There we go. So the intersection points that we have are at x equals 0 and 3. And you could verify that by setting the two equations equal to one another and solving for x. So we are going to rotate this region about the y-axis, and it's easiest to use cylindrical shells. So there is a typical rectangle that I'm rotating. Okay, so now the radius is still equal to x. The height's a little bit different, but it's not too bad. You see how the height of that little red box that I drew there is the black curve minus the red curve. So that will be 3 plus 2x minus x squared minus 3 minus x. So to find the volume, I integrate from 0 to 3. So circumference, 2 pi x, my x is the radius. The height is 3x minus x squared. The thickness is dx. Factor out the 2 pi, distribute the x, and we end up with 3x squared minus x cubed dx. Anti-differentiate, we have 2 pi times x to the third minus 1/4 x to the fourth, 0, 3, and that will give us 2 pi times 27 minus 81/4, which is 27 pi over 2. In many cases, cylindrical shells can actually result in a simpler integral than the disk method. Now, what if we rotate a region about the x-axis? What changes and when is this going to be useful? So if I rotate a region about the x-axis, something like this, say. So once again, think about the circumference, height, and the thickness. So in this case, the circumference is the distance from my axis of rotation of 2 pi. In this case, the r is equal to y. Now the height will be f of y, and the thickness will be delta y. And the volume will be an integral from c to d, so where this is, say, c, and this is d, so lowest y to highest y, 2 pi y f of y dy. Use cylindrical shells to find the volume of the solid obtained by rotating about the x-axis the region under the curve y equals root x from 0 to 1. So here is y equals root x, 0 to 1. So this region we're going to rotate around the x-axis. So we will slice this way. Okay. So the radius in this case is equal to y. The height, so how tall is that? Now it's not the case, so solve that for x, you get x equals y squared. That is the distance from here to here. That's y squared. The height will be 1 minus y squared. So to find the volume using this method, we will integrate from y equals 0 to y equals 1. Circumference, 2 pi y, height, 1 minus y squared, thickness, dy. That will be 2 pi times the integral from 0 to 1, y minus y cubed, dy, or 2 pi times 1/2 y squared minus 1/4 y to the fourth, evaluated from 0 to 1. So 2 pi times 1/2 minus 1/4, which will give you in the end pi over 2. On this particular example, cylindrical shells would have worked just fine, and cylindrical shells would have been actually easier. In that case, we would have sliced perpendicular to the axis of rotation, and we would have used the fact that the radius is root x, and the volume is an integral from 0 to 1 of pi root x squared dx, and that will give the same result. Next, let's use cylindrical shells to find the volume of the solid obtained by rotating about the x-axis, the region under the curve x equals 4y squared minus y cubed. So first you should graph this. Let's factor out the GCF, y squared times 4 minus y. So this curve will have y-intercepts at 0 and 4, and looks something like this. So this is the region that we will rotate about the x-axis. So we slice parallel to our axis of rotation. My radius is equal to y, and my height of my curve, it's a sideways height, but that height is 4y squared minus y cubed. And now the volume is given by the integral from 0 to 4, so think circumference, height, thickness. So 2 pi y, there's your circumference. The height is 4y squared minus y cubed. The thickness is dy. So 2 pi integral 0 to 4, 4y cubed minus y to the 4th dy. Anti-differentiate. That's y to the 4th minus 1/5 y to the 5th, 0 to 4, which gives you 2 pi times 256 minus 1024 and in the end we get 512 pi over 5. Lastly, let's consider some regions rotated about axes that are not the x or y axis. So we would like to find the volume of the solid obtained by rotating the region y equals x minus x squared and y equals 0 about the line x equals 2. So x minus x squared is a parabola, and let's find its x-intercepts, and it has x-intercepts at 0 and at 1. It's an upside down parabola, so it looks something like this. And the y equals 0 is the x-axis, so we're going to rotate this region about the line x equals 2. So let's draw in a typical shell. Okay. Now what's a little bit more tricky here is the radius. So this is my radius. So the distance from here to here, that's x. The total distance from there to there, that's 2. So in this case, my radius will equal 2 minus x. Not so bad. And the height of a typical a shell will be x minus x squared. So not that different. The only difference here is the radius is no longer just x. So my volume will equal an integral from 0 to 1. 2 pi, so circumference, 2 pi r, so 2 pi times 2 minus x, times your height, which is x minus x squared, factor out a 2 pi, and we're going to multiply together these two terms, which gives us 2x minus 2x squared minus x squared plus x cubed dx. And then anti-differentiate, and we have 2 pi times x squared minus 2/3 x cubed minus 1/3 x cubed plus 1/4 x to the 4th from 0 to 1. So that will be equal to 2 pi times 1 minus 2/3 minus 1/3 plus 1/4, or pi over 2. Next, let's consider what occurs when we rotate a region about a horizontal line. So we have the region bounded by y equals x squared and x equals y squared. And we are going to rotate this region about the horizontal line y equals -1. And we will use cylindrical shells. So there is my typical shell. Now, since I have a horizontal shell, I will need to solve both of these equations for x. This one's already done. This one we will have x equals root y. Now first, let's find the radius. So the radius is the distance from your axis of rotation to your shell. In this case, that is 1 plus y. The distance up to the x-axis is 1, and the distance from the x-axis up to the shell is given by y. Now the height of a shell, you have to kind of turn your head sideways and think that this curve is your top curve, the curve I just drew in red. And that is the curve that is root y minus the curve underneath it, which is y squared. Now let's find the volume. The volume will be given by the integral from 0 to 1. So circumference, height, thickness. The circumference will be 2 pi r, or 2 pi times 1 plus y, times the height, which is root y minus y squared dy. Or 2 pi is the integral from 0 to 1. And we distribute, we end up with root y minus y squared plus y to the 3 halves minus y cubed dy. And to differentiate, and we have 2 pi times y to the 3 halves, the coefficient of 2/3, minus 1/3 y to the 3rd, plus 2/5 y to the 5 halves, minus 1/4 y to the 4th, from 0 to 1. Now we input 1, and we have 2 pi times 2/3 minus 1/3 plus 2/5 minus 1/4, and you end up with 29 pi over 30.